Good morning, everyone, and welcome to this webinar on computational fluid dynamics applied on valves. My name is Alessandro Palmas, and I am a co-founder and developer at Conself, and I'm gonna show you today how to use our web-based CFD to perform a valve simulation. First, few words about Conself. At Conself, we help innovative small medium enterprises and freelancers in improving the engineering design of their products. We are doing this by providing design software easy to use and accessible everywhere. This is a list of our services. Our core business is for sure CFD on cloud. But we also offer consulting with dedicated development and tailored activities and product optimization. We also offer support with qualified technical personnel. We schedule events like these webinars and also provide training both on-site and remote served. But now let's talk about the most important product, the CFD on cloud. We are going to show you in a few slides how it works, and then we will apply it on a real valve simulation. Here you can see the advantages of having a CFD on cloud. With our solution, you can forget about license, paying just for the simulation you need, exploiting the software as a service approach. You can rely on cloud computing, so you don't need to have a high-performance hardware. With vertical application and automated workflow, the know-how is no longer a problem. It's a very simple approach, and you are going to see how simple it will be to perform a complete simulation. Finally, the budgeting activities are not required anymore, since you can charge directly the customer, since you are gonna pay just for the simulation you need. It translates in up to 90% savings with respect to the most common softwares already in the market. Someone may ask, why cannot just perform physical experiments? Well, simulations have a wide set of advantages with respect to experiments. In fact, the number of parameters you can analyze or the spatial and time resolution allowed by simulation is not comparable to those of experiments. Then the test scale, as well as the typology of the study you can realize by simulation, are very broad with respect to the experiment one. In fact, for example, you cannot perform an experiment with an explosion or a fire. It can be very dangerous, while with the simulation, you have a wide set of tools to perform this kind of analysis. Here we can see in 4 steps how a CFD simulation works on our platform. First, there is the geometry part with the creation of a CAD model, then the definition of a geometrical grid. Later on, you have to set up the CFD with the choice of the fluid model and the boundary conditions. And finally, you can analyze your results directly on your browser with our application. Let's dive in a little bit more in every step, starting from the geometry. We offer a wide set of input format available, like step file, IGES, and STL, in a different unit system, like in the international one and imperial one. We also perform an automatic creation of a wind tunnel for external flow, like external shape of vehicles optimization and also wings and airplanes. About meshing, we offer 2 different algorithms, like the hexahedral one and the tetrahedral one. We also provide a boundary layer for wall refinement, and we structured it in a simple way with a guided procedure that first allows you to perform a surface meshing and then the volume one. About CFD, we offer a wide set of choice. You can perform incompressible simulation or ideal gas one, that is a compressible simulation. You can analyze laminar or envisaged fluids, flows, or turbulent ones, relying on three of the most common turbulence models that are K epsilon, K omega, and Spalart-Almaraz. Finally, we offer both steady and unsteady simulation. One thing that we want to stress here is that we rely on OpenFOAM, so our results are very accurate and validated by the scientific community. About the results, we have the well-known ParaView application in its web-based shape provided on our web application. It allows you to perform a wide set of analysis with extraction of slice, streamlines, profiles, and contours. And so you can manipulate your data directly online. Even more, apart from the CFD software, we offer support available directly online. We have test cases and tutorials you can download and run yourself. You can find them on wiki.concept.com. Hardware resources are 24/7 available with potentially unlimited CPU power. That's the cloud computing at work. And finally, we can provide on-demand software development in case of specific needs. But now, let's talk about how to apply CFD on valves. And you will see from geometry upload to results analysis a complete simulation with our web application. This is the geometry we are going to use today. It's a common butterfly valve inside the pipe. And we will be focused mainly on the analysis of the flow inside the valve, and we will evaluate the pressure distribution as well as the flow lines inside this geometry. First thing to do is to prepare the geometry. The best thing to do with our software is to use a step file with colors. Colors can be used to define different boundaries, and as you can see here, they can be used for both boundary condition for the CFD side and also differentiation in the meshing part. In fact, we will have here three boundaries from the CFD point of view: one inlet with the red color, the outlet with the black one, and we will have the walls that will be the other part of the geometry. As you can see, in the part near the valve, we have at least three colors. We have cyan here, yellow, and a little orange that will be used to assign different surface refinement variables in order to differentiate the mesh from the zone far from the valve and the zone very near to it in order to improve the accuracy of our results. So now we are able to show you how to perform a complete simulation, and I will show you from the very beginning how to do that with our platform. So let's switch to a common browser. Here we are with this very standard browser. I'm using Google Chrome, and we are on concept.com, our home website. In order to log in into the application, just click on this button here. You will be redirected to the sign in or the registration. I already have an account. If you don't have it, you can just register here. So I will insert our credential with user and password and then click login. We will automatically be redirected to the application, and you can see there are two tabs, the dashboard one and the simulation. In the dashboard, there are some information about your account. The most common one is the one about credits. You can see the remaining credits and the used one. For the other part of the infographic, we will come back here later to have a deep understanding of it. So in order to perform a simulation, we just go to the tab where simulation can be set up here. And if you notice at the bottom left of the page, there are two buttons, one for the user manual, the other one for the contact support. Let's now define a new case. So butterfly valve, and we are going to create it from scratch right now. And now tap create. Here you can see, I'm sorry, just a second. We can create, okay. We can now upload the geometry we have here, upload. Then we have to define the file units, in this case meters, and how to group boundary condition. As I already said, we have defined different colors, so let's choose by curve color. This way we are gonna divide the geometry in depending on how it is colored. So we will click next. And then we have to define if the flow is internal or external. If you choose external, you will have to define a bounding box that will represent the wind tunnel, basically. In our case, it is an internal. So you can just click submit. And as you can see, confirming it, the step will be presented in cases in progress on your simulation tab. And you will see the progress bar here, moving from 0 to 100. And it will take a few seconds to load geometry. And we will see it in this select here. In the very moment it will finish. I already have a prepared case, so we are gonna skip this phase here. And okay, it's already finished. So it is this one, but I already prepared a webinar case, that is this one, and I'm gonna open it. As you can see, the geometry step have been run. So now we are in the second step, that is the surface mesh 2D. Here, first thing to do is to choose the step from which we have to start, and it's the geometry we just run. And as you can see, clicking on it, you will see your geometry in our application. At this point, you can see each of your boundary condition just selecting it in this menu. For example, let's choose yellow. That will be the valve itself. Clicking on yes, you can see here we have the valve. Because this was the part of geometry colored by yellow. You will find the whole set of boundary condition in that menu as well as in this select here. And for each boundary, you have to select it and to assign the two parameters defining the surface mesh. That is uniformity level and max element size. You have to do that for every boundary of this menu here. And then when you are done, you can just click submit. As in the previous step, it will be shown in the simulation case in progress zone. And once it will be ended, you can upload, you can enter the case and continuing towards the grid definition. We are going to skip this phase to save time, and we're going to go to Mesh 3D, where again we have to choose the step from where to start. So Mesh 2D just run, we choose it, and as you will see, we will have the very same geometry now here, but with a very important difference. In fact, we will have a refined mesh on our geometry, and we can see that choosing the representation as surface with edges. This way, you can see the body is represented with the mesh on it, and as you can see here, we have a different refinement in the near part of the valve. At this point, we are ready to perform the volume mesh. The volume mesh, we have two different algorithms. We are going to choose the tetrahedral one with boundary layer. We define here the maximum element size inside the domain. And then we have the boundary treatment. In order to understand better how it works, we can go to the user manual. And this is a manual that explains you how to use the web application. There are a lot of information. And here you can see difference between hexahedral and tetrahedral mesh, and here the boundary treatment. It's basically a definition how you want the mesh near the boundaries. So you can refer to the manual in order to choose the best thing for your case. And you have to define it for every boundary again, and then finally click submit. For this step 2, in order to save time, we're going to skip this phase and go to the CFD part, supposing that the Mesh 3D has been completed. In the CFD, again, you have to choose the Mesh 3D from where to start. And you will see here again your geometry, but now if you take a slice of your domain, and this is quite simple, you select system, then you apply this filter here and just represent it with edges as before in order to see the mesh. Click apply, and you will see here you have your slice, the slice of your domain, showing the mesh inside it. At this point, we can proceed to complete the CFD setup. The density model we want to choose is incompressible, as well as Spalart-Talmaras for turbulence. Then we have fluid properties and initialization, and we can have here the density, pressure of initialization, and velocity, and then the viscosity, and finally the Spalart-Talmaras variables. Proceeding, we have the boundary condition. So now, as we already saw in the slides part, we have 3 different types of boundary condition from the CFD point of view. We have an inlet, that is the red one, and here we assign a 0 gradient on pressure and a value in the variables for the velocity depending on how it is oriented. Since the inlet is oriented as -z, we can assign here a velocity of -0.5 in order to make it the fluid entering the domain. About the turbulence, the value you have to assign at the inlet can be evaluated using this kind of equation we provide in the manual. So now let's focus on the outlet, that is the black part. We can assign a standard pressure outlet, so a value for the pressure here and a 0 gradient for the velocity variables as well as the turbulence one. And finally, the other boundaries, cyan, yellow, dark orange, and light steel blue, are all walls, and here the default variables are okay. In fact, we have a zero gradient for pressure, a zero value for velocity, and zero gradient for the turbulent variable. So we are ready, and we can perform the final step, that is the simulation settings. Here you can choose between transient analysis or steady one. In this case, steady. Choose the number of iteration and the frequency you want the solution to be saved. Then again, you click submit and the CFD starts. We will skip this part and go to the results phase. Once the CFD is completed, you can go here and choose the CFD you just run, and that has been completed. The results will be loaded in your browser, and you can analyze them right online. You can see here the geometry. First thing to do is click on this small clock and go to the last iteration to have the final values for your variables. Then let's perform two things: a slice showing the pressure distribution, and then we will see the string tracing in order to show the path lines of our fluid. So let's start with a slice where we want to show the pressure, and we are gonna limit the range between 101.318 to the maximum in order to see the difference. Here you can see, here you have the inlet and then here the outlet, so there is a pressure drop here in the side between the first part, the inlet part, and the outlet part across the valve. We can again apply another filter, that is the stream tracer. Here you can see the streamlines. We can choose to color it. Oh well, first let's choose vectors as U, and then color it by U, and click apply. And we have also to redefine the legend, the range. So just limit the maximum value on 3. Clicking apply, you can see here you have the wall representation of your valve with pressure drop and the stream lines. As you can see here, there is a recirculation zone just behind the valve. And if you want to add the geometry, you can just turn on system and then scroll down in representation and changing opacity of system to value like 0.3. You can apply, you will see everything, the geometry, the slice, and the path lines represented in your browser. You can save your work, like choosing here the desired resolution, choosing capture, and then you can right click here and save your image. So this is how you can perform a complete simulation and analyze results directly online. And just a second spent on the dashboard, maybe it can allow you to have a deep understanding of these graphs here. You have, as you already see, there are 4 steps apart from results that needs the software to be run. It is geometry, mesh 3D, and CFD. Here there is an analytics reporting how many steps for each of these 4 you have run. And here there is the credits for the last 6 simulation. And so that's it. There is no more information in this page. And this was the presentation for the simple standard CFD simulation on Valve. But now we have something more. And just let me switch again to the presentation. In fact, we can show you an extended application that is a flow with particles. It basically consists in a valve where it's together with the fluid that can be air, water, oil, or anything else. You have also solid particles that can flow into your equipment, maybe like sand or something like that. In this case, there are at least two main aspects one wants to analyze, and are particle kinematics and trajectory calculation, as well as erosion rate estimation. So let's see how to treat both aspects. First of all, to track solid particles, one has to complete the following steps. First of all, you have to define the flow configuration, as we already did during this simulation here. So as in the standard CFD simulation, you have to define the flow, like inlet, outlet, and all characteristics like that. Then you have to define the particles in terms of density, number, their dimension, and materials. Finally, you can see how they move in the domain and how they interact with boundary and flow evolution. For the erosion rate, it is strictly linked with the collision between these particles and walls. And in order to evaluate it, you have to define the physical properties of both particles and walls, like density, Young modulus, and these kind of things. And finally, evaluate erosion rate on post-processing, taking into account the collision. We can provide both these features, and I'm going to show you both particle tracking as well as erosion rate estimation in a S-tube simulation. Just give me a second. I'm going to switch to the video. So here we have the video, and as you can see, after 1 second, there are many particles entering. Here there are 2 million entering the domain and flowing through the pipe, moving depending on the flow configuration as well as forces like gravity that acts on them. In this case, the gravity is oriented to has the z-axis. In fact, you can see that the particles are pushed down on the downside of the flow. And this is a simulation about tracking particles. And now I'm going to show you how to estimate the erosion rate. Just a second. You can see here that is ParaView with the post-processing. Here you can see the particles distributed in our domain, and I can eliminate them from the image in order to see how the erosion rate distributes in our walls. Here you have the outlet, here the inlet, and here there is the peak of erosion of our pipe, depending on how the collision between particles and wall happen. So that's it about the erosion. We can go back to our presentation. And now it's your turn. If you want to ask a question, here you can see how to do that. There is a small array of squares in the top right of your screen. You can click on it and then click on question and answer to ask questions. In the meantime, you are gonna write that. Maybe you have to be logged in Google Plus to do that. I'm gonna talk to you about how um, sometimes someone asks us questions like, do I need any particular hardware to run the web application? The answer is obviously no, since you can use a common web browser. It can be run also from a tablet, so a very simple terminal, and you can anyway complete the simulation as well as from your desktop. There is no limitation on the type of browser you are using or the operating system. The most common browser are supported, like Internet Explorer, Google Chrome, Mozilla Firefox, or Safari, as well as operating system like Windows, Linux, and OS X, as well as Android, as already said in case of you're using tablets, for example. Another question is how the subscription plans works, and we provide 4 different subscription plans from freelancer to enterprises. 2 of them are monthly based, and the other one are annually based, and they differ mainly in terms of a number of credits available that reflects directly on the number of simulation you can perform. We all are also open to custom solution. If you need it, just contact us. Here you can find our email and all our social accounts. If another question is, how does it cost to run 2 simulations at the same time? It's very simple. If you run them in serial or in parallel, there's no difference. If you have 2 simulations, 5 credits each, you can run them one and then the other one, or at the same time, it will cost you 10 credits, and that's it. If you want, you can also use the same account from different desktop at the same time. It means that 2 users can log into the application from 2 locations with the very same credential, and they will share a common workspace, and they can also have the possibility to share information directly online, allow for remote collaboration. About the accuracy of our results, as I told you during the presentation, we rely on OpenFOAM. That is a very well-known software, validated and developed in a high number of universities across the globe, and it has been used from Formula One race cars to industrial applications. So it's very accurate and trustable. This kind of simulation have been used in industry since the 90s, so it's not something new. The innovation is the fact that we brought this kind of analysis on cloud. In fact, it can allows you to cut costs up to 90%. We are going to make this kind of simulation available to every professional, and that's the innovative part of our software. If you want, we can provide you custom developments, in particular application that can be tailored for your specific needs. If you want a service like that, just write us a mail and we will get in contact very soon. We also offer support for new customer, and it can be provided directly online on the platform, So it's very straightforward, and we guide you through the completion of your simulation with very few steps and in a direct way. If there are no more questions, that's it. And thank you all for watching. Have a nice day.